All right, this problem says a leaky 10-kilogram bucket is lifted from the ground to a height of 12 meters. All right, so here's a picture of our bucket, and it's at a height of 12 meters. And then let's see, it's being lifted at a constant speed with a rope that weighs 8 kilograms per meter. All right, so this rope is 8 kilograms for every meter of its length. Initially, the bucket contains 36 kilograms of water. All right, but the water leaks at a constant rate and finishes draining just as the bucket reaches the 12-meter level. How much work is done? All right, so this problem is basically two little problems added up together, except they're not that little. All right, so the first problem actually is a standard rope problem. Okay, so all you're going to do is you're going to figure out how much work was. So here are the split up problems. All right, so one is dealing with the bucket with water, and then the other one is dealing with the rope. All right, so for the first problem, we're just dealing with the rope by itself. Like how much work does it take to move up that rope? All right, so this says right here, force on the ith slice of a rope. That just means how much force is applied to a slice on the rope. And that slice would be that red dot right there. All right. So we have here the mass density of the rope. Okay, so that just means like how much mass it has per every meter, and that's given to us in the problem right here. Mass density is 8 kilograms per meter. So that's our mass density right there. All right, so you have the mass density of the rope times the acceleration due to gravity, which is a number you have to know. 9.8 meters per second, and there should be a square right here. Okay, so this is not mass times acceleration, this is mass density times acceleration, which means you're not getting force, but you're getting force density. Okay, so this is force density, and then you have times delta x. And for this part of the problem, you can think of delta x as being the height of the slice of rope. All right, so dx, which is delta x, is the height of the slice of rope. So, which would be in meters. So if you're going to do, if you have force density times delta x, that all of a sudden together becomes force. All right, so that's force density. So like whatever, force per meter, right, times meter leaves you with force. All right, and then xi, or you could just say x, is the distance that this dot travels. So if that dot's there, it travels that distance. If that dot is there, it travels that distance. All right, and this is the work formula. So it's force, right? So here you have force density times the little piece of rope, the thickness of the rope. So that's like the force. That's basically the force applied on the dot. Okay, times the distance the entire dot is going to move. All right, now we use our integration. So we're going to go from 0 to 12 because it's kind of upside down. That's kind of how you do these, but the movement, this is 0. Well, it's moving up 12. Right, it's going from 0 feet to 12 feet, or whatever this thing is, meters. Okay, so we're going from 0 to 12, and you just put everything in here that we have from above. Okay, and this is just like the rope problem. If you're pulling up the entire rope, this is how much would be applied. I'm pulling up the entire rope. All right, so you multiply that out, you get 7.84. Integrate it. Okay, so luckily we have a 0 here, so the second half of the integration problem is easy. And we end up with 564.48 joules. All right, by the way, joules okay, I just dropped this up here. So a joule is equal to kilograms times meters squared over seconds squared. That's the unit for joules. And if you kept all the units in this whole problem, it'll end up in joules, because joules is the unit of work as long as you're dealing with kilograms, which we are, and meters, which we are, and seconds, which will just always be that way. So we have it in, that's the unit for work, will be in joules. Okay. And I also put the formula for newtons, which is right here. And newtons is the unit of force as long as you're dealing with meters, kilograms, and seconds. All right. All right, so moving on to, all right, so that's the force of the rope. Now we got to figure out, the work from the rope component of the problem. Now we got to deal with the bucket component of the problem, which is trickier. All right, so we know that the initial mass of the bucket is 36 kilograms. Let me see. Not really, actually. That's the water in the bucket, right? The water in the bucket. Let me erase this stuff here. All right, so the water in the bucket is 36 kilograms. And the bucket itself is 10 kilograms. So together, the bucket when it's full is 46 kilograms. All right. The final mass of the bucket, so when this bucket goes all the way up to the top, the bucket's mass is just the mass of the bucket without the water, which is 10 kilograms. So this is the mass of the empty bucket. All right, so let's see here. Force on the bucket will depend on how far we have lifted the bucket. Right, because the force applied to the bucket based on gravity and the mass is dependent on how much water is in the bucket. And as the water is leaking out, there will be less and less force applied to the bucket. All right, so the first thing you want to do is you want to get the leak rate. The leak rate is, we know that this thing starts at 36 grams. That's when the bucket's, that's the max water, right? So the max water is 36 grams. And all that 36 grams gets cleared out in 12 meters. So we know it's leaking at a rate of 36 grams per 12 meters, which reduces to, or I think I said grams, but 36 kilograms per 12 meters, which reduces to 3 grams per meter. Okay. What we're going to do now is we're going to figure out the mass of the bucket, per lifted meter. All right, so it's going to get lighter and lighter and lighter. So you could think of like your y-intercept, if you were doing like y equals mx plus b. The y-intercept would be your starting value your starting value when x is 0, right? So in this situation, the most amount of mass we're possibly going to have is the initial one, and that's going to be, when x is 0, it's going to be 46. So you're going to have 46, and then you're going to subtract out your 3 kilograms per meter times however many meters you do, right? So if you do 0 meters, this is a 0, I'll just color in like that, and it's 46 grams. If it's 1 meter that you've gone up, then this becomes 1, right? And you have, this will become a 1. So then it's going to be 3 times 1, which is 3. Then it becomes 46 minus 3, which is 43 kilograms. And if you do all 12 meters, then you're just going to be left with your initial 10 kilograms, which is the mass of the bucket. All right, so x is the distance the bucket moves. This is the initial mass, bucket and water and all, and this is the decreasing rate, and this is times the distance that the bucket moves. So this is, the equation above is the mass per lifted meter. Now, that's mass per lifted meter. Okay, so now we're going to figure out force per lifted meter. Remember, force equals mass times acceleration. All right, so we got the mass part right here, right? Acceleration, you use acceleration due to gravity, which is 9.8 meters per second squared. So that's your acceleration. So now we have our force per lifted meter. Let me just erase this. All right, so we have our force per lifted meter, which comes out to, I just took the units out right here. So cleaning it up a little bit, we have that. If you distribute it in, all right, so you end up with 450.80 minus 29.4x. Okay. Now this part's kind of confusing. So this force is not constant, right? So this is, so if you plug in x, right? So this x right here, this x represents the height that the entire bucket's gone up, right there. So that's the height that the bucket's gone up. All right. So if you want to figure out the force at any given level. Okay, yeah. So this is the force per lifted meter, and what you're going to do. Wait one sec. Okay, explain this again. So this becomes the force per lifted meter, right? So you distribute, you do your 9.8 meters per second times this guy up here. Then you end up with force per lifted meter. Okay, which simplifies to this right here. But this force is not constant. Okay, what that means is the force is always changing. And so what you need to do is you need to kind of think about like a little slice right here in the bucket. Okay, and this little slice is going to move a tiny little distance. And that movement, that tiny little distance is dx. So the work that is applied to that little tiny little movement is your force, that's right here, your force per lifted meter, okay, times your small move. So, and I wrote here, but this force is not constant. It's the same for a very tiny amount of time. Okay, so this force right here is this value for a really small period of time. So we have to break up this force into tiny little movements. And those tiny little movements are going to be dx. They're going to have like a dx length. And then we're eventually going to add them all up. But for one tiny little movement, it's dx. All right, so then you multiply your force, your general force equation right here, times your small move. All right, and that's the work for a very small move. Then the next thing you do is you're going to say, all right, well, I'm going to add them all up now. I'm going to add up all my little small moves. I'm going to do my small moves from 0 to 12. That's how high we're lifting the bucket. So from 0 to 12, you're going to add up all those small moves. And you're going to use you're going to take the integral, you use your force for any value of x, times your tiny movement, but then you're going to add up all those tiny movements in this integral, and you basically work that out. All right, so luckily this is 0 down here, so the second half of the integral is good. And this is the work from the bucket component. Then what you got to do is you got to add the bucket component, which is right here, which is this number right here, right? Plus what we figured out earlier, which was the rope component, the work from the rope component. And that goes right here, and then this gives you your answer. and it's going to be in joules since it's all in kilograms and meters and seconds, which is 3,857.28 joules. And that's it.